Tonight we're going to learn about how to represent reactions, well, you already know how to balance, but how to represent this balanced equation and what does the coefficients mean. We're going to remember how to do a mole ratio. We're going to remember molar mass, and we're going to do examples of simple calculations. And then we're going to learn limiting and excess reactant and more practice problems. Okay, so representation of reactions. We already know that we are going to start with the reactants and that the arrow is going to separate the reactants from the products. We're going to, the symbols or the letters that appear in parentheses are going to be the states of matter of the compound. So in this case, everything is gas. And we're also going to have the coefficients, which are the balanced equation, what we use to balance the equation. So the plus sign separates two or more formulas from either the reactants or the products. The arrow is what separates the reactants from the products. We could have heat in the form of a triangle and the states of matter, and we also can have the AQ symbol, which means dissolved in water. So that is used for solutions. Okay, it is common to represent the reactions with the shapes of the molecules. So this is a CH4. Now, if this coefficient, these two, we need to show two molecules of oxygen. So we're going to represent the particles, but also the counting of the molecules. Why is this useful? Because it would be very evident that the equation is balanced. We're going to have the same atoms on both sides of the equation. In here, we have one carbon, on the products, one carbon. We end up having 4 atoms of oxygen, and in the products, 1, 2, 3, 4 atoms of oxygen. And then 4 of hydrogen, also 4 of hydrogen. Okay, so this is going to be a representation. You're going to see them commonly represented in books with these kinds of diagrams. Okay, so what does these coefficients of the balanced equation, what do they really mean? If we're talking about small scale in the equation, they mean molecules, like individual items. For example, this is 1 molecule of methane, 2 molecules of oxygen, which react to produce 1 molecule of carbon dioxide and 2 molecules of water. Now, as we know, atoms and molecules are very small. So it would be very, very difficult to work with atoms and molecules. So that's why we use the term of the mole. The mole is a unit of measurement in chemistry. Do we remember what a mole is? Who can tell me what is the concept of the mole? Excellent, Nicole. Correct. It's a unit of count. Excellent. And do you remember how many? Another example of a unit of count, it's dozens, and dozens would be 12 units. In this case, the mole, how many units are we talking about? Remember that it's a very big number because since atoms are very small, we need a lot of them to work with them in the lab or to see them. Somebody remembers that number? Okay, I'm going to help you. 1 mole is 6.02 times 10 to the power of 23 things. Exactly, Fer, you got it. Exactly. 6.022 times 10 to the power of 23. So this is a huge number. So that's how many particles a mole represents. So in chemistry, we work with these units instead of small scale units. Okay, this is what I call the Bible of stoichiometry, or the Bible of chemistry. These will tell us what things do we need to do to work stoichiometry problems. For example, if you're given its particles, like it could be molecules, it could be ions, whatever particle, and you need to change to any other thing, the first thing that you have to do is use Avogadro's number, the one that we just talked about, in a ratio of 1 mole to 6.02 times 10 to the 23 particles. By doing this, we're canceling particles and getting moles on the numerator. So now that we have moles of our given, we're going to use the mole ratio found in the balanced equation to change from A to B. The only way to change from A to B is through moles. We cannot change with any other unit. But once we have moles of B, then we can change to any unit that we're asked for. So we can change again to particles using Avogadro's number, or to grams using the molar mass, or to volume of a gas using the gas laws, or to solution, volume solution using molarity. In the same way, we can receive our given in any unit. The main idea here is that the given should be changed to moles to be able to change to moles of the required. We're going to do some examples, so don't worry if you are still a little bit rusted in this concept. You will get it very, very easily. Okay, so the first thing that we need to do, this is the central part of the problems. We need to be able to learn how to change or how to do the mole ratios. And this is actually very simple. You get the coefficients of the balanced equation, and then you can relate any compound of the equation to any other. So for example, we have 1 mole of methane. We can relate it to 2 moles of oxygen because we have the ratio of 1 to 2. We can also relate 1 mole of methane to 1 mole of carbon dioxide, and we will have this ratio. Also 1 mole of methane to 2 moles of water, and we will end up with this ratio. And the same thing with all the combinations possible. So now we can do 2 moles of oxygen to 1 mole of carbon dioxide, 2 moles of oxygen to 2 moles of water, and lastly, 1 mole of carbon dioxide with 2 moles of water. We can have it on this format or in the reciprocal, depending what we need on our particular problem. Any questions about the mole ratios or how to get them from a balanced equation? Okay, excellent. We're going to move on. Another very important skill that we need to solve the stoichiometry problems is remember how to get molar mass. Remember, molar mass refers to the amount of grams we have in 1 mole of a particular compound. And a reminder of how to get these numbers is to search in the periodic table for the mass of each element. The mass of each element, for example, carbon is 12.01, hydrogen is 1.01 times 4 because we have 4 atoms, and then we add them up, and we will end up with this number, 16.042 grams of methane. So 1 mole would be equivalent to this many grams for methane. And then we can do the same for all the compounds in a reaction. And again, we can use it like this, or we can use the reciprocal, depending on what the problem is asking. Any questions of how to get molar masses, or where do we find these numbers? We're fine, right? Okay, we're going to move on. So let's start with problems. Let's suppose that we have the same equation and they're asking us how many grams of carbon dioxide can be produced when 20 grams of methane react with oxygen in excess. When you see this concept, oxygen in excess, it means that you don't need to worry about oxygen because you will have enough for the reaction. So your focus should be on the other given. So 20 grams of methane. So we are going to use the grams, the given grams, go through this path and go to the molar mass to get the grams of the required. So we're going to focus on that section of our diagram. So we are going to start with our given. What would be the first step? To change grams of methane to what? I'm going to show you again the diagram. The grams of methane, you need to use the molar mass to change to moles of methane. Very good. Excellent, Nicole. So we are going to use the molar mass to do this. And a very simple way is to place on the numerator the unit and the label that we need to cancel. So we are canceling here grams of methane, and we have moles of methane on the numerator. What would be the next step? To change moles of methane to what? Okay, we're going to change now to moles of the required, to moles of carbon dioxide. And the way to do that is to use the mole ratio. And in this particular reaction, we have a ratio of 1:1. So that's why we're placing here a 1:1 ratio. Once now we cancel moles of methane and we have moles of carbon dioxide on our numerator. The last step would be to change to grams. And again, we're going to use the ratio of the molar mass now of the required carbon dioxide to get our answer. If you notice, when do you know where to stop? When you have the units and the compound that you need. So by doing this process, we cancel grams of methane, we cancel moles of methane, we cancel moles of carbon dioxide, and our unit that is not canceled is the required. So that's how we know we're done with all the ratios. So then we use our calculator, but then we need to check our sig figs. How many significant figures do we have on the given? Exactly, 3, so that's how many we need to show on our answer. So we round to 54.9 and we're done with the problem. Okay, let's do another example. Practice problem number 2. Excellent. At a winery, glucose in grapes undergoes fermentation to produce ethanol, and they give us the formula, and carbon dioxide. How many moles of glucose are required to form 124 grams of ethanol? So now here, notice how the given is grams, but the required is moles. So a way to think about it is, it's again this setup, but we're going to stop. We're not going to use that last step because they're asking us for moles. So this will be a shorter problem because they're only asking for moles. So how do we change grams of ethanol? What do we need to change it to? We need to change it to moles of ethanol, right? So what are we going to use? What ratio should we use? How do we change? We need to reach 2 moles of ethanol. So we're using the molar mass, right? The molar mass from the values of the periodic table of ethanol with a ratio of 1 mole of ethanol. And then we're going to use the mole ratio. I'm sorry, here there's a mistake. It should have been a 2 here on the bottom. I have a mistake here on the slides. I will correct it. Let me correct it right now. So this one, this is incorrect. It should be 2 moles in here. So just let me check that the math is correct. Maybe I also did a mistake on the math. So it's going to be 124 divided by 46.08 divided by 2. So my answer here would be 1.35. Let me move this. 1.35. Okay, sorry about that mistake. We need to make sure we are using the proper ratios. In this case, it's 1 mole of glucose. That one was correct. But it's 2 moles of ethanol. This was my mistake. And now we have the correct answer. Any questions on this corrected problem? Okay, we're going to move on. Okay, another example. Acetylene, and we have the formula C2H2, is used in welder's torches. It burns in oxygen. How many molecules of oxygen are needed to react with 22 grams of acetylene? And we have the reaction right there. So now we're changing grams to molecules. So what do we need to do? We're changing grams. We're going to start here. Molar mass to reach moles, moles of the required, but then we're going to go to molecules. And we're going to ignore the rest of the options. Is this clear? Okay, it makes sense, right? We're changing grams to moles, then using the mole ratio, and then going to Avogadro's number. So let's do that. We're going to start with grams of acetylene. We're going to use the molar mass to cancel grams of acetylene and now have moles of acetylene. Then we're using the mole ratio of 2 to 5. 2 to 5 right here to cancel moles of acetylene and get moles of oxygen. And lastly, we're going to use Avogadro's number because now we need to cancel moles and get molecules. Any questions up to here? Okay, so excellent. So then we get our calculators. Don't forget the exponent on the calculator. And then this is our final answer considering 3 sig figs as in our given. Okay, so it's pretty easy. Just follow the diagram, and in no time you wouldn't even need the diagram to change from one to know what to do. Okay, so now let's go to the concept to limiting and excess reactants. The limiting reactant will be the reactant that is used up first, and it will stop the reaction. And it will limit the amount of product that can form. So the product depends on the limited reactant. We're going to use a simple example, a sandwich. For example, this image has lettuce and tomato and cheese, but we're going to ignore that. We're going to make a very simple sandwich. Only 2 slices of bread and 1 slice of ham. We're going to do a simple sandwiches today. But we went to the kitchen and we only have 8 slices of bread and 3 slices of ham. So we're going to run out of ham before we run out of bread. Does this make sense? So now the limiting reactant will be our ham. And we can only make 3 sandwiches. We cannot do more because we don't have, sure, Santiago, you can think of it as a remainder. So you will have in excess the slices of bread. So now you can only form 3 sandwiches. So your limiting reactant is the ham. the one that ends up first. Make sense? So the concept is as simple as this. So let's do an example with this kind of concept. Suppose that we have again the same reaction, and now they're asking how many grams of carbon dioxide can be produced when 20 grams of methane react with 20 grams of oxygen. Notice how they're giving us two given, and both of them are reactants. So this is a hint that we need to figure out which is the limiting reactant first. So the process is the same. We're going to change grams to grams. But now we need to think of the concept of the limiting reactant. So you start with one reactant, do the same as before, molar mass. You can stop in moles of that reactant, do the moles of the other one. And here, at this point, you can decide which is the limiting reactant. If the ratio of the equation is 1 to 2, if methane you have 1.25, how much would you have of oxygen? You would have double of this amount, right? You will have 2.50, but you have much, much, much less. So oxygen would be your limiting reactant. Or you can think about it the other way around. If you have 2 units of oxygen, you will need half of that for methane. So if you have 0.625, you will need half of that, so 0.3, and you have much more. So whichever way you think about it, you should get to the same conclusion, that oxygen is your limiting reactant. It will run, like you will run out of it first. Does it make sense up to here, the concept of the limiting reactant? Okay, so this is a way to think about it. Decide in the terms of moles which one is the limiting reactant, and then continue the problem only with the limiting reactant. So we already decided that it was oxygen, but they're asking us for grams of carbon dioxide, so we have to move on. So only now that we know that the limiting reactant is oxygen, we do the process with oxygen, and that's how much carbon dioxide will be produced. Another way to do these problems, another way to do it is to continue both processes until the end, to change grams of methane all the way to grams of carbon dioxide, and to change grams of oxygen all the way to carbon dioxide as well. And then you check the two products, and you would choose the smaller amount. And the smaller amount of product will be given by the limiting reactant. And we got to the same conclusion, that oxygen is the limiting reactant. You can never do 54.9 grams of carbon dioxide because you will run off of oxygen first. So your product is determined by the limiting reactant. Any questions here? No questions. Okay, we're going to practice then another problem. We're going to move on to another problem. So let's do this next problem. Titanium is a strong, lightweight, corrosion-resistant metal that is used in rockets, aircraft, jet engines, and bicycle frames. It is prepared by the reaction of titanium 4 chloride with molten magnesium at those temperatures. And we have the reaction right there. And then the givens are: in a certain industrial operation, 3.54 times 10 to the power of 7 grams of titanium 4 chloride are reacted with 1.13 times 10 to the power of 7 grams of magnesium. Now here it says how many grams of titanium are theoretically produced. What is the percent yield? It's 7.91 times 10 to the power of 6 grams of titanium are actually obtained. In this problem, now they're adding another concept, the concept of percent yield. So whenever we do these calculations in chemistry, we are doing it in paper. So that's a theory. In theory, that's how much we will get. But on the real thing, we can have, maybe we didn't control the temperature, maybe the pressure was not the best one, maybe we didn't have the proper conditions, the catalyst. So most of the time, we will get less product than expected. And a relationship of the expected and the real one is what is called the percent yield. So we're going to use this problem to approach that concept as well. Okay, but first we'll have to solve. Okay, let's do the given. We're going to do a process of grams all the way to grams. We're going to organize our data. So we have the grams of the reactants, and we're going to ignore this for now. The grams of the product actually produced is going to be ignored, is going to be used until the end. So we're going to focus right now in how many grams of titanium are theoretically produced. So the same as before, we have to analyze. In this case, I chose to analyze both of the reactants at the same time. So what's the first step when you have grams of the given? What is the first step? Change grams into what? Do we need the diagram again to remember? Thank you, Santiago. Exactly, Fer. We first need to change grams into moles using the molar mass, the value of the periodic table, and consider every single atom involved. So we use the molar mass for both, and now we have moles on the numerator. The next thing that we're going to do is to change moles of the given to moles of the required with the mole ratio of the equation. So for titanium, it's going to be a 1-to-1 ratio, but for magnesium, it's going to be a 2-to-1 ratio. So we placed, I'm sorry. In here, I'm going to do the same thing as decide here, which is the limiting. And also we think about it that way. If this is the how much moles we have in a 1 ratio, we need to think about how many will we need for magnesium, and we will need double of this amount. Do we have double of this amount? We actually have more. So up to this point, we should be able to conclude that titanium 4 chloride is the limiting reactant. Now, this is one way to solve the problem. Another way is to solve both reactants until the end. So if you wish to do that, you can only work with titanium 4 chloride from now on, or you can move on with both of the reactants. So this is what I did next, to move along with both of the reactants. And finally, using the molar mass to get grams of titanium for both. And then how do we analyze this problem? We choose the one that gives us the lesser amount of product. So by doing this, the lesser amount of product is given by titanium 4 chloride. So we got to the same conclusion of the limiting reactant in excess, and we have to choose the grams that are the less from both processes. Any questions from here? Okay, so we're going to move on. So as I mentioned before, all these calculations are theoretical. We don't know the conditions that the reaction has to take place on. So on paper, like in theory, this is how much we'll get. But they're telling us that that was not the case. They're telling us that this amount, less amount of product were actually produced. So the percent yield, it's a ratio of the actual yield and the theoretical yield times 100%. So we do that and we will get that this reaction worked at an 88.5%. Does it make sense that the percent yield is smaller than 100? Should we ever have percent yields greater than 100? Does it make sense? We cannot have percent yields greater than 100 because we cannot produce more, like we don't have enough mass to produce more of the theoretical. So my percent yield should always be smaller than 100%. Of course, the closer you are to 100%, it means that you are very efficient. So that's what you will want. You will want percent yields close to 100, but it will never overpass 100. Does this make sense? Okay, so we're going to move on to another problem. So this problem, I took it from the Math and Science at Work. Here is the link if you want to go through it. It's very interesting. And it talks about how they deal with carbon dioxide in space shuttles. So the space shuttles uses an absorption method to remove the carbon dioxide. As you know, if we breathe carbon dioxide, that's toxic to us. So the astronauts need to get rid of it to avoid getting intoxicated with their own carbon dioxide. So on the shuttle, the absorption of carbon dioxide is accomplished with a chemical reaction using a sorbent, something that absorbs, that is known as lithium hydroxide. Lithium hydroxide is an attractive choice for spaceflight because of its high absorption capacity for carbon dioxide and the small amount of heat produced in the reaction. You wouldn't want a lot of heat in such a small space. Disadvantages include the irreversibility of the chemical reaction. This causes the replacement of lithium hydroxide canisters to be a daily activity during space shuttle flights. There is also the potential for some toxicity within the space shuttle cabin due to the lithium hydroxide dust that could be ingested by the crew. So I found this really interesting. Let's go now to the problem. So the CCC, the contaminant control cartridge, which contains the lithium hydroxide, is used to remove carbon dioxide from the space shuttle cabin. We have the equation. Here we have a photo of the astronauts changing these canisters, which has to be done daily. A typical space shuttle crew consists of 6 individuals, and each CCC contains 750 grams of lithium hydroxide. Assuming that each crew member expels 42 grams of carbon dioxide per hour on average, and that a mission is scheduled to last 18 days, how many CCCs must be carried on board on the space shuttle? Okay, so let's organize our data, and of course it's going to be a grams to grams problem again. So we organize our data, and that's what we have. The first thing that we need to think about is which one should be or which one is our limiting reactant. Which one you wouldn't like to run out of? Okay, carbon dioxide, Santiago, should be our limiting reactant, right? So you do not want to run out of lithium hydroxide. You cannot have the carbon dioxide in excess because then that will be toxic for the crew. So you need to consider carbon dioxide to be the limiting reactant. Okay, so now that we decided the limiting reactant, that's obviously the one that we have to start with. So they told us that 42 grams of carbon dioxide were expelled per hour per person. And we have an 18 days mission. So one day has 24 hours, and then the mission is 18 days. This is per person, so we need to multiply times 6 because the crew is of 6 people. So this is the amount of carbon dioxide that is expelled in total, in the total mission. So this is the one that we are going to start our stoichiometry problem. So we have the grams of carbon dioxide. We change to moles with the molar mass. We change to the lithium hydroxide using the coefficients of the balanced equation. We change to grams of lithium hydroxide using the molar mass. And that's how many grams of lithium hydroxide we need. And then they gave us another data in which every CCCs contain 750 grams of lithium hydroxide. So we do this ratio of every CCCs 750 grams, and we will get this amount. So since these are units, doesn't make sense to use the sig figs. It makes sense to make a count. So you will need 158 CCCs at least. That would be the minimum because the carbon dioxide that they gave us was an average. I will certainly would like to take more, right? Because you don't know if it's going to be a stressful day or I don't know. I wouldn't want to be in a situation in space where I will run out of these cartridges. So 158 would be the least amount that the mission has to take into space. Any questions about this problem? Okay, we're going to move on to the last problem that I have for you tonight. And this is the last problem. Okay, it says the following reaction proceeds until the limiting substance is all consumed. So we have the reaction right there. Right now, this time is aluminum and magnesium 2 oxide, which will give you aluminum oxide and I'm sorry, it's not magnesium, it's manganese. Manganese 2 oxide, which will give you aluminum oxide and manganese on its own. So a mixture containing 110 grams of aluminum and 200 grams of manganese 2 oxide. Notice that they're giving us both reactants. That should be a hint that we're dealing with limiting reactant. Was heated to initiate the reaction. Which initial substance remained in excess and by how much? And they're asking how many grams of aluminum oxide can be produced. So again, we're going to do a process of grams to grams. So we can, again, I am going to do the process for both reactants at the same time. We're going to change grams to moles using the molar mass of each. And then moles to the mole of the product with the mole ratios. And then the molar mass of the product. And then we have these two answers. Which one should we choose? Which one is the best answer for the product? The bigger amount or the lesser amount? Correct, Santiago. We should choose the one, the smaller amount, the 95.82 grams. Right, because then our limiting reactant is manganese 2 oxide, because that would be the reactant that gave me the smallest amount of product. So yes, this is the amount of product that was produced, and we concluded the limiting reactant, but now our answer, because they ask us which reactant is in excess and how much of it remained after the reaction. So aluminum is a reactant in excess. What we do next is start again with the limiting reactant, the 200 grams of the limiting reactant, and work our way now to get how many grams of aluminum would actually react with this amount of reactant. So we're going to do the same process of grams to grams, but now from manganese to oxide to aluminum. So we're going to do the same. Grams to moles, moles to moles of the required, moles to grams. And this is the amount of aluminum that reacted with the 200 grams of manganese oxide. So then we just do a subtraction with the original, and we will have the amount that remained after the reaction. So now we're done with all what was required from this problem. We can conclude that aluminum is a reactant in excess, that 59.29 grams of aluminum remained after the reaction, and that 98.82 grams of aluminum oxide was produced. Any questions? Okay, so from my part, that is all. Thank you all for your attention. And remember, I'm sorry, Irene. I'm still not sure I understand how to know which is the limiting. Okay, Irene is asking how to know, how to realize which one is the limiting. Okay, Irene, we're going to start from here. Okay, you can do this process in two ways. You can change the grams of the reactants to moles of the reactants. That's one way to do it, and then decide from there. Or you can do the process from grams of both reactants to the product that they're asking you. So that's what we're going to do. If we do this process, we are going to have two possible answers. And my best answer would be the smallest amount of product. If you think about it, if we go back to the simple example of the sandwiches, the limiting reactant there was the ham, and we could only do 3 sandwiches, even though we had 8 slices of bread. So your product depends on the reactant that will run out first. And the way that you can tell is that the reactant that gives you the smallest amount of product, that one is your limiting reactant. So in this reaction, with this amount of reactants, you will run out of manganese oxide first, and you will have aluminum in excess. Irene, is this better? Or should I go back to the simple example of the sandwiches? Okay. So once we decided that this is the best answer, this is not our answer. We're going to ignore this answer. And now we can classify our reactants as the limiting and as the excess. So in here, we can conclude that this was produced, and we can identify the limiting and the reactant in the excess. Now, since they ask us how many remained after the reaction, this is where we start with the limiting again, and now do the ratio towards aluminum, towards the excess reactant. Why? Because this is going to tell us how many really reacted of aluminum. And the difference is the one that was in excess. Right? Like the extra bread for the sandwiches. This is what was extra after the reaction proceeded to completion. Okay, and then we can have our 3 answers that were required. Any questions? Okay, so from my part, that's all. Remember that you can email me if you have any other questions or you get stuck in solving a problem. Don't hesitate. I can help you through the email. Thank you. Good night, everybody. Bye-bye, Irene. Thank you, Fer, Santiago, Nicole. I see you tomorrow in class. And everybody else, I can see you again in the next stream. Bye-bye.